Okay, let's go to the last presentation of the whole session, the last one, but the best one maybe. From the Netherlands for sure. Thank you. Welcome.
Okay, welcome everyone, and thank you all for sticking around for the end of the day. I appreciate it. My name is Kim de Wit, and I'm a PhD candidate at Utrecht University, and also part of the LOS Living on Soft Soils project. And I'm going to talk about reconstructing Holocene regional background substance in the Netherlands using interpolated. So you hear me now? Yeah, that sounds better. Yeah, okay. Sorry about that. Should I can just continue it. Yeah. Okay. Then, the background substance and not the soft soil substance that many of my LOS colleagues are looking into. And I want to start talking about the water table rise, because relative water table rise can actually tell us a lot about regional substance. And I want to show this using this figure here, which is the relative sea level rise over the Holocene for the region around Rotterdam and near where we are, here in Delft. And we see here on the x-axis the age from 9,000 years ago to 2,000 years ago, and the relative sea level rise on the y-axis. And it's important to take into account that relative sea level rise contains both sea level rise components, such as the melting of ice sheets and tidal changes, but it also contains background subsidence components, such as these basin subsidence and isostatic processes. And we can, if we look at these relative sea level curves, we can actually see this when we look at here in blue, you actually see the same curve from the western side of the Netherlands, but now there are also some other curves from the south, so near Belgium, and also from the north. And when you look at this figure, you actually see that they're not all at the same level, but there's a difference. And within the Netherlands, this relative difference is already about 4 meters for the middle of the Holocene. So there's a difference in subsidence that occurred in the north compared to the south of the Netherlands. And so what is causing this subsidence? At present day, there are, roughly speaking, two main components. And I've divided them here in this schematic figure. I made them the same color because at present day, they're roughly at the same rate. But that wasn't always the case. So on the left, I've put the basin subsidence component, which is roughly at the rate of 1 to 2 decimeters per 1,000 years, or 0.1 to 0.2 millimeters per year. And this rate is stable throughout the Holocene. While on the other side, we have the GIA signal, or the peripheral glacial isostatic adjustment signal, due to the fact that the Netherlands is in the periphery of the former ice sheets in Scandinavia and Scotland. And this signal is more varying over the Holocene. So it was higher at the start of the Holocene, but due to the viscoelastic process, it is now decreasing. And we know this because already quite a few studies have been done for this around the Netherlands. So on the left, for the basin substance, we actually have a pretty good idea of what it is, based on studies by Coy et al. In 1998 and an expansion of that by Cohen et al. In 2022. But on the right, I've put some figures of different modeling studies for GIA. And what you see is that the rates and the location of the different rates is quite similar, but not all. There's still some differences between the different models because they all use different input models and slightly different calibrations. So we actually need something else to know what is the best suited model for the Netherlands. And for that, we need observations. And in our study, we use geological water table observations. So what's that? Well, the main source for the water table observations, for that we use basal peat layers. And the reason for that is that this basal peat layer is the first peat layer that grows on top of the Pleistocene surface. You can actually, this is a picture for the subsurface of Urk, also in Flevoland. And what you see is the Pleistocene dune. And when the sea level was rising, the water level inland was rising with it. And at some point, the water level reaches at a high enough point above the surface that peat started to grow. So if you now dig into the soil, you take a core and you get a sample of this transfer, this moment, this transfer point, and you date this, you actually get the point in at which time this water level was at this depth in the subsurface. And if you do that for several points, for example, on top of a Pleistocene dune, you can make a water level curve or a sea level curve like I showed in the beginning as well. And in the Netherlands, a lot of this basal peat layers have been collected and dated, and not only for sea level rise, but also for other types of studies like delta morphology or other types of paleo studies. And so we have a lot of data, but it's not all in the same format. So one of the things we did for our project is to actually try to create a more unified collection of all the data that is suitable for these water level reconstructions, and unified more into one data set. So now I want to talk a bit more about the methods I used for creating a spatial temporal interpolation of this data, and I also briefly want to go into some results, some first results that I got out of it. So again, this is all the water table data we have, the geological data. And again, here are some sea level or water level reconstructions that have been done in the Netherlands. And traditionally, these are done at single sites, but because we want to look, and that's because they want to reconstruct the sea level, for example, at one location. But we want to look into more regional subsidence processes. So we actually want a better coverage of the spatial and the temporal, better spatial and temporal resolution. So therefore, we created an interpolation of the data. And this is what you see here in the middle. It goes at 1,000 years time steps, just showing the water table as reconstructed by this, based on these water table points that I showed in the last slide. And the nice thing about this is that you can still make these, you can still make these H-depth plots at single locations, but now you can also make them at all the locations in between, and you can do some more spatial analysis based on the whole, the whole plane actually. So I briefly want to show the method, the concept of the interpolation. These are just some more technical details, so I won't go into them too much. But the idea is that we actually interpolate the water levels of these observations between low stand and a high stand in a normalized grid. And it's also what you can see here. There's the low stand level and the high stand level. And then the interpolation goes in between this. And another important thing to know is that the equation exists of a sigmoid and a linear component. And the sigmoid component mimics sort of the water level rise that is increasing at the start of the middle of the Holocene, and then it slows down more to the late Holocene. And the linear component also includes part of this linear differential subsidence that we see. This is one of the components, but this is also in this part, so it's a bit complicated in that sense. So that's on the interpolation methods, and now just to show some output of what you can get out of it. One back, yes. So this is again like the animation I showed before, but then filtered to show only when the water level is above the Pleistocene surface. So you can actually see that around 8,000 or 7,000 years ago, it starts to rise above the surface even more. But there are also some areas that are consistently already above the surface, and this has to do with the subsurface, and some other factors. And actually, to study the regional subsidence patterns, we want to filter these out. So I'm actually working on this right now. So this is a first attempt to filter out these regions using a slope function and a minimal water level depth. So if you do that, you see that here, for example, at 6,000 years ago, this is the total grid, but already filtered for the shown above the Pleistocene surface. And then if you filter the part that's actually more controlled by the sea level, then you only this part remains. And what I did now is to show, get an estimate of, again, the differences between the north and the middle of and the south of the Netherlands. I took the average of these regions and compared the age depth fields, which are over here. And then you see a little bit a similar idea of what I showed in the beginning, but now based on the interpolation output. And this is, the blue line is the north, the Wadden Sea area. The yellowish line is the sort of North Holland and Flevoland. And then the black line is more the south of the Netherlands, Zeeland and South Holland. And again, you see that the north is lying lower than the middle and the southern part of the Netherlands. And then here on the right, I actually took the difference between the south, so that's sort of the zero line, and then calculated the differences between the other two regions. So then you actually see, again, this 4-meter difference that I showed in the beginning. You see it also based, but then from the interpolation output. And when you compare it to 3 minutes, okay, I'm almost at the last slide, so that's fine. And then I've put this figure from Keaton et al. In 2002 below here, which also has a similar comparison. In the black line here is actually was mean sea level in Belgium, and then the dashed line is the western part of the Netherlands. And he also put in the tectonic rate, which is this linear envelope. And what you can see is that only part of the subsidence is explained by this tectonic rate, but you also see a decreasing, so they come closer together. And this is probably this glacial-isostatic term that is not linear, but decreasing over the Holocene. And that's exactly almost actually what we see here as well. And also one of the things that we want to do is also take this tectonic component into account and see how the results are then. So to conclude, what I just showed was that there is a difference between the middle and the late Holocene if you compare the different curves. So in the middle, actually, the difference is larger, and in the late Holocene, all the curves are closer together because of this decreasing trend. And well, you see a clear difference between the north and the south, but I just showed that. And apart from that, I talked about using a data-based approach for relative sea level reconstruction for the Netherlands. And also I showed the first step of using this to actually study long-term regional subsidence. And the last remark I want to make is that we did this independent of these modeling studies, the figure I showed at the beginning of my presentation of these different glacial isostatic modeling results. And the nice thing of that is that we actually are trying, the next step is to combine our results with what they are doing to find out which JA model is actually the most suitable for the Netherlands. And then if we have that, we can also use that to make better predictions for the JA related subsidence in the Netherlands for the future. Yeah, so with that, I wanted to, sorry, doesn't work. I just wanted to acknowledge all the consortium partners from our LOS project. And yeah, I want to thank you. And if you want to contact me, here is my information. So thank you.
Thank you for the nice presentation. We have time for questions.
Thanks, Kim. Interesting talk. I think it's very essential to do for every area in the world, for the total subsidence budget. So I was wondering, okay, I haven't done my homework yet, but you showed a study also from Cohen 2022 about the tectonic subsidence.
Yeah.
Is it after that study still assumable that the tectonic subsidence is linear? And if not, how does it affect your analysis?
I'm not sure what you mean, but I think if I understand correctly, I think in the study from Cohen et al, they, at least for the Netherlands, well, they made an expansion of the study done by Kooi et al in 1998. And I think, from what I understood, is that the rates in the Netherlands didn't change too much. So it's still, I think, the same, yeah, it's quite similar rate. So I think it's still a sort of a linear term, or at least over the Holocene. Yeah.
Okay, thanks.
Thank you. Very nice. Just one question that I really don't understand. How you must quantify this groundwater paleo data? How this number has been derived? From which data? This is something that I don't understand well.
Let me go back. Please. Do you mean this part, or that's?
You say the groundwater.
Yeah, it's a bit. The term for it is maybe a bit unclear. What I actually mean is the depth of which the water level, these water level indicators. Wait. So this is the paleo groundwater level as we see it now in the subsurface, but that's actually, yeah, it's so it's the mark as we see it now. So it's actually the relative water level after all the subsidence that happened after this peat has grown. So I hope that understands your that answers your question.
Probably yes. So and then do you take into account that, let's say, that the yellow boundary then can move differently depending on which is the load above it from point to point, and this can affect then your data interpretation, right?
That is one factor. That's why we try to use this basal peat because it's on top of the Pleistocene surface, and we sort of assume that it is that it's somewhat stable compaction, that there's not too much compaction of the subsurface. But of course, yeah, there might still be some, so there is an uncertainty in that as well.
Thank you.
One question is on the maps. So you have the boreholes, then you create the maps. Is this a creaking process? How you connect these? Or?
So yeah, first what we do is actually we first we fit this trend to all the observations that we have, and then you already get a surface like a 3D grid from this trend, and after that we perform, I didn't mention it now because of the time, but we actually take the residuals from this trend and the observations, and with that we also do another kriging step to get an even closer interpolation that's even closer to the observations where it's possible. So it's a bit of both, but it's first the trend function and then another kriging step.
Okay. Also, so spatially you also creaking then.
Yeah.
Okay, and would for instance salt tectonics could that play a role as well?
Yeah, that's something that I'm also looking into this because with all the data that we have, I've tried to make it now that we actually have take into account the natural compaction of this layer, but also the tectonic tectonic movement, but also human-induced subsidence. So probably like salt. Wait, sorry. Did you say salt?
I said salt tectonics, so diaparism.
Yeah.
So actually,
No,
the movement of salt in the subsurface
Yeah.
by nature and.
Yeah. No. Now that I
Okay.
started talking about
It's
it.
okay.
Yeah. No. So we try to take into account the different components and then correct for this as well.
Okay.
Yeah.
Thank you.
Other questions? Okay, no. Okay.
Okay, thank you very much.